In mathematics, the derivative is a fundamental tool that quantifies the sensitivity to change of a function's output with respect to its input. But what is a function? In mathematics, a function from a set x to a set y assigns to each element of x exactly one element of y. But what is a set? A set is a collection of different things that are typically mathematical objects. But what are mathematical objects? A mathematical object is an abstract concept arising in mathematics. Typically, a mathematical object can be a value that can be assigned to a symbol and therefore can be involved in formulas. Commonly encountered mathematical objects are. Hello, everyone! If you have ever found yourself in that kind of situation before, then welcome to the third episode of our series called Calculus for Dumb Babies. In this series, I will try to teach you guys calculus in a way that is simple and intuitive. So, whether you are just like a primary student who is interested in the concept, or maybe you are someone who may have graduated but haven't really touched the concept in a while and wants to revisit some of the ideas, this series would be perfect for you. In this episode, we'll be going over some of the essential concepts about derivatives, continuing from the first and second episode about the overview of the calculus and the limit notation. So if you haven't seen both of the episodes, you can click on the I on the top left or right hand corner or click the link in the description below. And don't forget to give me a like, subscribe, and comments if you enjoy my content. So with that said, let's begin, shall we? Okay, so let's start off with a recap for the first two episodes that we have been through, right? So for the first episode, we actually looked into two separate problems that actually relate to the two fundamental idea in calculus. So for the first idea, it was the idea about integration through the problem about the area of a circle. This problem was proposed by the Greeks. And the second was the problem about the speed meter, which is like when you drive a car, you can see the speed meter, right? Yeah, and this actually leads to the fundamental idea of what we call differentiation or derivative. For the problem about the area of the circle, one of the philosophers, which his name is Archimedes, actually came up with a really clever solution. So basically, he divided the circle into 8 slices and then he rearranged these slices into a shape that resembles a rectangle. So for 8 slices, it's going to be something like this. You can notice that as we increase the number of slices, we actually got a shape that looks even more like a rectangle. And so as the number of slices increase to like infinity, we will actually get like the perfect rectangle. And that is how Archimedes actually compute the area of a circle. And this idea of actually just kind of cutting into small pieces and then summing it up together, that is the idea of integration that we look at on the first episode. The second problem is about the speed meter. The thing with the speed meter is that your car actually displays the speed at every moment in time, right? When you drive a car, you look at the meter, you can see immediately of what speed your car is actually on. But when we examine the definition of speed again, we can find that speed is actually the change in time and the change in distance, right? But we can't really have a change at an instant. So that just kind of leads to the question of how your car actually determines the speed at every position, while the definition of speed literally has to have more than one position at a time. Your car actually performed a really clever trick of actually just moving a very small amount in time. So if that small amount in time is something like 0.01, and then compute the change in distance divided by the change in time of that small interval, this is like the fundamental idea of what we call differentiation or derivative. Now, in the second episode, we are trying to find a way to actually properly define this operation. And one way we initially did is, since we have infinitely many slices, we can write, we made like slices equals infinity, or we have change in time really close to zero, right? So we can write change in time equals zero. But that is actually mathematically wrong because you can't really have a value equals infinity. And similarly, you can't really have a value divided by zero, which is 1 over 0 or something like that, which is mathematically wrong. So we were trying to find a solution that can actually help fix this problem. And that is why we define the notation of what we call limits, which is instead of we saying the slices equals infinity, we can say that the slices approaches infinity. not infinity, but approaching infinity. Similarly, for the change in time, we can say that the change in time actually approaches zero, not equals to zero, but approaching zero. And that way, we can properly define this kind of phenomenon. We also look at how to write this notation mathematically, and this is how we write it mathematically. So, for example, if we have the area of the circle, right, and divide it into n slices, can be like 8 slices, so n equals to 8, 16 slices, so n equals to 16, and 32 slices, so n can equals to 32, and on and on and on. And what we are saying is if we make the slices approaches infinity, we can write LIM as an arrow infinity. Something here will equals to the area of the circle. And similarly, if we increment the small time step in the distance of our graph as h, we can say that, okay, as h approaches zero, then we can compute the speed with this notation right here. In this episode, we'll actually explore on how we actually will be writing formal mathematical definition of derivative. Okay, so in the previous example, we have been referring to this kind of graph using the things in the real world, right? The speed of the car, the speed meter, or something like that. Those are examples in the real world. But in order to determine the formal definition of the derivative, we have to get a bit abstract into the mathematical world. So let's do that. And you might see that in this slide, there are a lot of technical terms that I haven't actually talked about before. So let's look at some of these technical terms one by one so we have a clear understanding of what's going on. All right? So let's start off with this thing right here, slope. What is a slope? When you think of slope, you can think of like a mountain, right? And the mountain has this kind of slope. So basically, if the mountain has not much slope, it's going to be a bit kind of flat. But if there's a lot of slope, it's going to be something like 90 degrees or something like that. And that is really like the same thing as what we looked at in the previous example as speed. Because in this example, we have y as like the vertical axis and x as the horizontal axis. And so the slope is really the change in y divided by the change in x, which is literally the speed in like the previous example. In mathematics, we express this change of y divided by the change in x in this notation right here. It might look up scary, but the character is called delta and is actually referring to change. So basically, this is the ratio of change in y divided by the change in x. This is written as delta y divided by the delta x, which is change in y divided by change in x. This is a bit kind of like a mathematical convention. So we have already established what slope is, right? And slope is essentially the same thing as speed, but in a more general context. It's also sometimes, if you're actually talking about time, so may also be referred to as rate of change. If this x-axis is actually referring to time, this will be called rate of change. Like for speed, it's actually the rate of change in distance. So I just want to give you a bit kind of terminology with this one. It's basically just like a more general way of saying speed, something like that. All right. Okay, so with that out of the mind, what is this thing right here? Well, this thing is what we call functions, and it's literally the same thing as writing y. Basically, function has a lot more benefit when you are actually analyzing the graph. For example, if you have a lot of graph, by denoting it as a function, you can kind of like identify it much easily. Like you can use f of x, g of x, or h of x, and it's much easier than just using y1, y2, or y3 for different graphs. Another benefit is that for functions, when you want to evaluate the value at a specific position, for example, if I want to say find a y value at x equals 3, if I have like a standard y notation, for example, y equals maybe x squared, if I want to evaluate y at point 3, I may say like, okay, y at x equals 3 equals something, right? But that notation isn't really that compact. So in calculus, a lot of times we just denote this as f of 3. And this means that we have a function fx and we evaluate it at x equals 3. And the reason why it's called functions is because you input something and then it outputs something. In this case, you input in x and it's output y or something like that. So that's a bit kind of like overview of the things we will be actually working on. And so with this setup, we can now find a way to derive the general equation for the derivative. And the way we do that is like what I did for the first episode, but just a bit more general. What I mean is this. So in the first episode, we're trying to find the speed, right? The change in y divided by the change in x. And so in this case, what I can do is, instead of speed, I can write slope. And that equals to the change in y, which I would denote here delta y, divided by delta x. And since we use this function notation, right? And so if we have a point, any point x, right? We want to know its y value, then its y value is going to be f of x, right? Because in this graph is defined with the equation of f of x. And so with x input, the output is f of x, the y value is f of x. And if we move a small step in time, say h, right? This is like the same thing like what we did in the previous slide, h approaches 0 or something like that. So if we move a small step in time h, the x value here is going to be x plus h, right? We just kind of move it h, and so the x value is x plus h. And then the function here is going to be the same thing. It's going to be this f evaluated at x plus h, which we write like this. And so for the slope, we can just write it as this equation because when we talk about change, we talk about minus, right? And so the change in y is this f of x plus h minus f of x divided by x plus h minus x. And this is just taking these and minus them together, taking these and minus them together, right? And you can see that x minus x is actually 0. And so we end up with this expression for the slope. So this is the expression we have for the slope, and this slope applies to any point. It can be any point, all right? Since we say that h is actually approaching 0, right, in the definition of derivative, what we can do from now is just plug in the limit, and that is the definition of the derivative. So what I mean is this: limit as h approaches 0, because we want h to approach 0. And so f of x plus h minus f of x divided by h. And that, my friends, is the formal definition of the derivative you will find in the first page of every textbook that talks about derivative. It's a bit kind of complicated. I mean, the notation seems really scary, but if you understand that it is just slope, and since we want h to approach 0, and so we define limit to be that way, and yeah, that's it. We have already derived the main definition of derivative. We can denote the derivative with a couple of symbols. The first symbol we can use is we can just put this kind of prime symbol between like f and brackets. X is one of the ways that is often represented in textbook that talks about calculus. Another way we can do it is doing something like this instead, df by dx. This is my way of thinking, and d is just kind of like the difference, right? Because we minus them together. So basically this notation just kind of like implies that there's a difference between the f divided by the difference between the x, and that difference is very small. And so this notation, in my ways, I think is a bit more intuitive, and this is also a notation that is more common when you go into general fields. For example, if you go to physics, you go to maybe chemistry, in kinetics, or in finance, or even in mathematics, like in ordinary differential equations or something like that. And so in this teaching, I will actually be using this notation right here, but just remember that this one is also valid as well. With this definition in hand, let's just look at the example that we already worked with, which is the function f of x equals to x squared, which is just x times x 2 times. All right, so this is the exact same function that we derived the speed in the first place, right, for the first example. And so with this definition, I want to try to rederive the expression that tells you the speed at any moment again. Let's do that. The derivative of this, right, it is equal to limit as the step in time h approaches 0 of f of x plus h minus f of x divided by h. And since in this case we know that our function f of x is equal to x squared, by extension we know that if we move a tiny step h, f of x plus h would also equals to x plus h squared, right? And so we can plug it into this formula right here. We get a limit as h approaches 0 of x plus h squared minus x squared divided by h is going to be our derivative. And from this, we can do the same algebraic expression that we did in the first episode, which is limit as h approaches 0 of x squared plus 2 times x times h plus h squared minus x squared divided by h. And so we can find that x squared and x squared just kind of cancel each other. Since this is like divide, right? And there's one h here, there's h squared here, which is just kind of h times h. And there's h here, we can cancel these, and cancel these. And so what will remain is limit as h approaches 0 of 2x plus h. And since this is a limit as h approaches 0, and so this is actually approaching 0, so we can take this out to be 0. And so we get the final expression being 2x. And that, my friends, is the derivative of this function right here. You can write it as df by dx, or write it as f prime of x. Those are two valid ways of writing this. You can see like there's a value of x here, right? And so you can substitute in different value of x for different positions you want to evaluate that derivative in. For example, if I want to evaluate the derivative at point x equals 3, we can just substitute in this value. So basically we can find that df by dx at the values, we can write a line here at values x equals 3, that will equals to 2 times 3, which equals to 6. And that is the derivative at that position. And you can substitute in any values that is on that graph. Another cool thing about derivative is that this value here, 6, right, is actually the same thing as the slope of a tangent line. So basically, a tangent line is a line that touches the graph exactly at the point, something like this, right? The line is actually just touching exactly at that point. This 6 here refer to that slope of this line is actually equal to 6. And the slope of 6 is this line is literally the same definition as before, the change in y divided by the change in x of that line. So this is a bit kind of a visual representation of what we actually done at the point x equals 0. The derivative, of course, since this is 2x, is going to be 0. And so the slope of the line at this point is going to be 0, which just means it's going to be flat in the xy plane. All right, it's going to be this flat line right here. Now, I want to point out a misconception that a lot of people have when they kind of visualize derivatives. For example, this is the same graph as in this picture. I just rewrite it as slight variation of the example we started with. So this is the same graph as like our car moving with the speed meter, but I just use abbreviation here. So S here is actually distance, and you can see distance is actually here, and T here actually refers to time. Since in the previous slide, what we did is we find the derivative at the point equals 0, right? Instead of f of x equals x squared, we have s of t equals t squared, and so we can write ds by dt at point t equals 0, that will equals to 2 times 0, and that equals to 0, which is like the point here. My question is, since the speed at the beginning is 0, is the car actually moving at time equals 0? I let you think for a minute.
A few moments later.
The answer is that the question doesn't make sense, because when we talk about time equals 0, it means that we are talking about a specific time, right? But moving means that we have two specific points in time, because you can't really move at like a single moment, you know, you have to have two instants in time. And so this question is just kind of invalid in a way. And that is because when we find derivative, we isn't really finding the exact speed at a point, because that is impossible to do. But what derivative is actually telling you is the best approximation of the speed around that point. That is the real meaning of the derivative. So I write this for you to see. It's the best approximation of the speed around that point. So this is a bit I would think I want to know with derivative is that you can compute like for every point in time, right? But what essentially that value represents is the best approximation of the speed around that point. It's not the exact speed at that point, all right? Just note this thing right here. Because if you think that derivative is like the speed at that instant point, then, I mean, the car isn't really moving, is it? It's going to get a bit confusing. And so I just want you to note this thing right here. And now, let's talk about a more complicated thing. So we look at x squared already, right? X squared is x times x twice. Now let's look at a more general case, which is f of x equals x to the n. N here being any number like 1, 2, 3, 4, 5, and so on. Basically, it's a more kind of like general form. And so I want to ask you, how do we take a derivative of this thing right here? The answer is we just do the same thing. So we have the definition of derivative, right? So it's just the same thing. So df by dx, that equals to the limit as h approaches 0 of f of x plus h minus f of x divided by h, right? And in this case, f of x plus h, that will equals to x plus h to the n. And so in this case, we can write this as limit as h approaches 0 of x plus h to the n minus x to the n divided by h. And from this point, what we can do is do this exact same thing that we did for the previous example about x squared. So this is just raised to the n. And in algebra, we also has this kind of theorem that we can expand x plus h to the n. And that would actually result in x plus n x to the n minus 1 h, and then plus on and on and on, and it's going to end up at h to the n, and then minus x to the n divided by h. We can cancel the terms that has the most power, and since this one is divided by h, right, and every term in here has a h, and therefore it's going to be nx to the n minus 1. So basically the h for the first term will be gone, and plus something that has h. So basically this will be limit as h approaches 0 of nx to the n minus 1 plus something that has h in it plus something that has h in it, and so on. And since we tell that h is approaching 0, and therefore the only term that is remaining is a term that doesn't have h in it, and that is nx to the n minus 1. And that is a derivative of f of x equals to any n power. And this is actually a very common formula that it actually has its own name, which is called a power rule. And I think if you learn about derivatives, this is probably like the first formula you will actually learn in class of how to compute a derivative. But what I want to highlight here is, even though the expansion might be complicated, since we have limit as h approaches 0, we can just ignore all the other terms that has h in it at the end, and just the only term that is remaining is the first term, which just simplifies everything. And so yeah, I think that's partly one of the beauty of limits, is that you can just kind of ignore all of them at once, just like they were a 0, even though they're not. All right? It's very complicated, but what I want to point out is how we actually approach it. We just approach it with a definition of derivative, like what we did for the last time, and that's all. And so that is like one of the most basic functions that we can compute derivative of. But if you learn in like calculus 1, there are a good amount of more complicated functions, like for example trigonometric functions or exponential functions. Trigonometric, I mean things like sine, cosine, tan, or something like that. And exponential, it's 2 to the x or something like that. And for logarithm, it's a bit kind of like inverse of exponential. There's also things about that. You can add, subtract functions and actually take the derivative of that, or multiply functions together and take a derivative of that, or divide functions together and take a derivative of that. There are a good amount of formulas that is associated with these kind of operations, but I'm not going to talk about in this video. There's also things like composite functions. Like if you have ever heard of chain rule before, this is like a very popular rule for calculus to actually approach composite functions, which is literally just kind of stack two functions together. Like for example, in this case, x plus 2 squared. You can view this thing as like maybe y squared, y equals to x plus 2. And so it's just kind of like a two functions stacked together. Like there's a square function here, but there's this thing sandwiched in between. So that's kind of like the idea of composite functions. And there are a good amount more things that you need to learn if you're actually going to do this course. So I just kind of want to point it down here as a disclaimer, but I think if you understand like the main idea behind what I talk about for the x to the n, or for like the general concept of derivatives, I think you can have a much easier grasp of this concept. I would just also want to point out another common functions of finding a derivative, which is to find the minimum and the maximum values. So for example, this first function of sine of x, which you don't really have to know what it is, but what I want to point out is that the function just kind of curves, something like this, right? We can use derivative to actually find where the maximum point is, which is this point, and where the minimum point is, which is this point. Notice that since we thought that derivative is the tangent line, right? And since on top, the tangent line is just like a straight line in the x-axis. Straight line means like the slope equal to 0 because there's no rise in y. And this one slope is also equal to 0 because there's no rise in y. And so what that means is that if we compute the derivative at these two positions, the value that you can get from it is 0, and therefore if you're able to find the derivative of this, so basically you can just get the df by dx of this, and you can put it equal to 0 and then solve the equation, you can get the exact maximum and minimum point of that function itself. So that is one of the things that is really commonly used with derivatives. For example, if you want to find the solution in your maybe physical system or something you are working with that has like the highest value or the lowest value, then you can actually use derivative to find those values themselves. And so that's one of the really common application of derivative I want to highlight. And yeah, that's it for like the overall thing about derivative. A lot of it is more on like how you actually compute it, like how you actually deal with weird function of derivative. I've actually already kind of talked a lot about what derivatives actually is for the previous two episodes. So I think there's not much content going on in this episode. It's just kind of like how we derive this formula more mathematically formal. So yeah, that's it for this video. I hope you actually got a good grasp of this concept. Derivative is actually not that hard because, I mean, if you understand what slope means, derivative is just that. If you enjoyed the video so far, don't forget to give me a like, subscribe, and also comments. All right? And yeah, that's pretty much it. Thank you so much for watching, and I see you in the next episode about integration, which is going to be the final episode of this series for now. So that's it for this video. Thank you so much for watching, and bye!